This section is about the cross product. So the cross product is one of the products you can find for two vectors. The first one is the dot product, and the second one is the cross product. So if you have two vectors, so let's talk about the definition of the cross product. If you have vector A to be, we're going to do three space, A1, A2, A3, and vector B to be B1, B2, B3. So we have two vectors in three space. That's a 3. Then the cross product of A cross B, and they're always vectors, so you're looking at the cross product of two vectors, is given to be a vector Now it's defined to be A cross B equals the vector A2, B3 minus A3, B2, A3, B1 minus A1, B3, and let's move this over a little, A1, B2 minus A2, B1. I would not memorize this. It comes from the determinant. So let's keep this here and let's talk about A cross B. So what we do with A cross B, this truly is the cross product right here. It's this vector. So if we take A cross B and set up the determinant with I here, J, K, and then in it we put A1, A2, A3, B1, B2, B3, then we find the determinant. Now remember, I'm just going to run through this. We start with the plus I, and when you start with the plus I vector, that means you pick up the I and you throw out the row and the column that it's in to do the cofactors. We're going to, remember we would draw a line down from that circle and across. I can draw it when I erase it again in the video, it's gone. So for example, we have I, J, K, A1, A2, A3, B1, B2, B3. So when we circle this I, we cross off the row and we cross off the column. So when we write our cofactors underneath, we're going to write I, and the cofactor matrix is A2, A3, B2, B3. And then we're going to pick up the J, and the signs alternate, so this is always a minus J. And again, we're going to cross off that row in the top column, the top row, and now we're going to cross off the middle column. So the left for the cofactors are A1, A3, B1, B3. I wrote that weird, I know. And then we have plus K, and in this case, we would cross off the top row again in the last column. So we have A1, A2, B1, B2. Now remember that to find a determinant, let me switch to my pencil here. Remember that to define a determinant, we multiply down and keep the sign, and we multiply up and change the sign in a 2 by 2. So that's going to drive what we're doing here. We're going to multiply down and keep the sign, and we're going to multiply up on the up diagonal and change the sign. We're going to multiply down and keep the sign. We're going to multiply up and change the sign. So let's run with that. And when we do this, down here we have A2, B3 plus, and up here we have minus A3, B2. Now you could call it B2, A3, but remember that the elements in their vectors are real, therefore the commutative property holds. So I'm going to scroll this up a little bit. We're going to say we have I times A2, B3 minus A3, B2. We have minus J, and when we follow this down diagonal here, we have a plus, and we have A1, B3. And when we follow the up diagonal, we have a minus A3, B1. So we have A1, B3 minus A3, B1. And on the last, let's put plus vector K. And on the last one, when we follow the down diagonal, we have A1, B2. When we follow the up diagonal, we have A2, B1. So we have parentheses A1B2 minus A2B1. So if we put that into a matrix and into the, not a matrix, but the vector format like above, we have A2B3 minus A3B2. And then we're going to distribute this negative on this one and call it A3B1 minus A1B3. Now, if I was doing this on my paper, I'd just say minus A1B3 plus A3B1, because what you're really going to have there is a constant, so it doesn't matter. So I'm going to write it in this format like, so it'll match up above. And then for the third element of this vector, we have A1B2 minus A2B1. So as you can see, it matches the vector we have above. It is the same vector. And most people who are figuring A cross B write a 3 by 3 matrix and find the determinant. I don't know anyone who has memorized that definition up above. So your best bet when you're finding a cross product is to write your 3 by 3 matrix and find the determinant of that 3 by 3 matrix. Now, some people say, when I find the determinant of a 3 by 3 matrix, I like to write my 2 rows repeated and find my matrix that way. You can do it just the same, it'll work. Remember, you're going to go up means that up you get negative values, you change the sign, and down you get the positive values. So you could go either way on that. As long as you know how to find the determinant of a 3 by 3 matrix, you're good. And if not, we walked through it very slowly there. So hopefully it'll make sense. Let's look at an example. And it says let A be the vector 1, 3, 4, and let B be the vector 2, 7, negative 5. So what we want to do is we want to find A cross B. I'm going to use cofactors because I like it that way. I used to always teach it with rewriting my 2 rows, but cofactors are actually, you tend to lose things less. You tend to be more precise with your cofactor method. So I'm going to write ijk at the top, and then your elements of A come next, and then your elements of B, 2, 7, negative 5. So I'm going to write it over here to remind you, because this program is weird. When I erase, it erases it from everywhere. So when I circle a row, when I circle an element, I also cross off the row and the column. This one is the column up and down, and this one is the row. And it always goes plus when you pick up the I, minus when you pick up the J, and plus when you pick up the K. So we're going to say plus I, understood plus. And when we cross off that top row in the first column, we have 3, 4, 7, negative 5, minus J. We cross off the top row again, and we have 1, 2, 4, negative 5, plus K. We cross off that top row again in the last column, and we have 1, 3, 2, 7. So now we're going to actually do the matrix determinants. I'm going to draw my lines like this, first of all, minus and plus, because I'm switching writing utensils. So while I'm here, I have a minus and a plus, and then I have a minus and a plus. And if I were doing this on paper with you on the board, this is exactly what it would look like. So let's look at I. So I have plus, but what I really have here is a minus 15. And then up here, I have a minus, and we have 28. So minus 28 and minus 15 makes a minus 43. Now let's look at we're going to say minus J. And I have a plus down here, so I keep the sign, and we have a negative 5. And when we go up the diagonal, we have a negative because we always change the sign. So that'll be negative 8, so that gives me a negative 13. And then we have plus K. And on the down diagonal, we have a plus 7. And on the up, we have a minus, and that makes 6. So that makes a 1. So if we were to rewrite this, we would say negative 43I plus 13J plus 1 understood K. Now, it was given to us in the nice, pretty vector format. So we want to answer in that same format of -43, +13, +1. We tend to answer in the same format we were given unless it states otherwise. Actually, WebAssign might prefer the IJK. They should indicate which answer they want. Normally, whatever format you are given, that's the answer you want to give. So in my opinion, that is the best answer right there. Okay, so now we have some interesting information about cross products. We have a theorem, and it says the vector A cross B is orthogonal to A and B. To both. I guess we should put the word both in there. I'm not sure why, because in my opinion, that's kind of implied. But the vector A cross B is orthogonal to both A and B. So this picture helps you see that A cross B is perpendicular to both A and B. See the perpendicular markings there? So now they have a right-hand rule. This is the right-hand rule. And the right-hand rule says that if your fingers turn the same way as the angle between A and B, then you set your hand right there at that point on A cross B, and the thumb points the direction. So set your hand on there and actually think about the fact that then that angle is coming out towards you. Now, if we were to take and turn it the other way, then in order for your fingers to follow that arrow on your right hand, your thumb has to point down. Therefore, it would be going into the screen. So we say it's coming out of the page or into the page. In this case, it's coming out of the screen or into the screen. And there are problems that ask you that, so you need to understand it. Hopefully that makes sense. So let me remind you again that this right here, we're following this angle, and there will always be an angle between them, and it will be marked. So the way your fingers curl needs to follow that arrow. So as I curl my fingers, they're curling towards me, and my thumb is pointing up. Now, in order for my fingers to curl the red direction, my thumb has to point down. So that's the difference between going into the page and out of the page. It's kind of a very cool. It's a very cool way to remember which way you're going out or into the page. Now let's go ahead and put this next theorem here. And so it says, remember that our vector has both length and direction. So this theorem comes into that. It says if theta is the angle between A and B, between the vectors A and B. So if theta is the angle between vectors A and B, now remember that vectors A and B, we're going to be talking about sine, so we're looking at acute angle. So we're going to say, so theta is between 0 and pi. But if you think of it in terms of a triangle, it makes sense. Then the length of the cross product, then the length of A cross B is, we have the length of A cross B, which is interesting there, because first you need to do the cross product, and then you need to find the length of it using the square root of the component squared, equals the length of A times the length of B times sine of theta. So if we have A cross B, we can find it, but we can use it to find sine. We can use this formula to find theta. We can use it for lots of things. So there's a pretty proof of it. I'm not going to do it for you. I happily will if you email me and ask me. I will send it to you. And we have a corollary that goes with that. Now remember, a corollary means it is not as strong as the theorem. It follows directly from the theorem. It's not strong enough to get its own note. So we're going to say two non-zero vectors, A and B. They have to be non-zero for this to work. Two non-zero vectors, A and B, are parallel if and only if. Oh, see, we like this if and only if, IFF. It's time to learn to write that. If and only if. We talked about that biconditional statement before, but if and only if A cross B equals 0. Now, an if and only if, that comes from up above. So an if and only if means the if then this way, and the if then this way. So we can say, we're going to read the first if then. So two non-zero vectors are parallel if A cross B is 0. And we're going to read it backwards and say, I guess the if would go here. If A cross B equals 0, then two vectors are parallel. So an if and only if is a great conditional statement because it can be read both ways and used both ways. So that's important here. Since the vector is completely determined by magnitude and direction, we can now say if we have non-parallel vectors A and B, like in this figure here, A cross B is the vector perpendicular to both A and B, and the orientation is determined by the right-hand rule. The length of the vector is given up here. The length of A times the length of B times sine of theta, and that's exactly how, this is what physicists use right here, is A cross B equals this. Now let's look at the parallelogram that I've drawn here. And let's talk about this area of the parallelogram. This is a very important application that we have here. So the area of the parallelogram equals base times height. Now if you look at the base is the length of A times the height. Now this is a right triangle, so we could say that this height equals the length of B times sine of theta. Pause for a second and think about how that really truly came about. That length is the length of B times the sine of theta. Oh, there should be a vector notation there. So we're going to say the base is the length of A, and the height is the length of B times sine of theta. So our area of a parallelogram can be found of two ways. We can say the length of A times the length of B times sine of theta, or we can use our definition and say that's the length of A cross B. So both of those work and help us be able to find the area of a parallelogram. So this is actually a note that's often made, the length of the cross product. So let's put it here, note. I know I did it backwards. Do you need me to bring it over here? Let's do it this way, note. There we go. So the area of a parallelogram formed by A and B. Area of parallelogram. So we have an example that goes with that. Let's just keep going here. Let's bring it here. So we have an example, and it says, find the area of the triangle. Remember, a triangle is a half a parallelogram, so we're good here. Oops, triangle. With vertices, I'm not going to write all the words. With vertices, P is 1, 4, 6. Q is -2, 5, -1. And R is 1, -1, 1. So in order to find our area of a parallelogram slash area of a triangle, remember the area of a triangle equals 1/2 the area of a parallelogram. Parallelogram, box, whatever. All right, so the first thing we need vectors A and B. So we're going to find vector A to be P times Q, to be the vector PQ. So that means we take Q minus P. So -2 minus 1 is -3. 5 minus 4 is 1. -1 minus 6 is -7. And then we're going to do PR. So let's let B be PR. And we get 1 minus 1 is 0. -1 minus 4 is -5. And 1 minus 6 is -5. So we know from up above that to find the area of our parallelogram, we can find A cross B. So we're going to find A cross B and then take half of that. So let's say A cross B. Remember, we're finding the area of a triangle, not a parallelogram. We have IJK and -3, 1, -7, 0, -5, -5. So we're going to take I, and we're crossing off the top row in the first column. We have 1, -7, -5, -5, minus J. We cross off the top row. We have -3, -7, 0, -5, plus K. We cross off the top row in the last column. We have -3, 1, 0, -5. I literally cross them off lightly with my pencil so that I can make sure I do it correctly. So now I need to mark my arrows with my pluses and minuses. And I do, and I'm your math teacher, so you might want to as well. I've done this for lots and lots of years. This is not a newbie thing. It just helps me remember to do it correctly. So I'm going to switch colors here. Here I have a -5. So when I multiply these two, first of all, I have a negative here. When I multiply these two, it makes a positive 35. So this is going to be a -35. This gives me minus 40i. Now I have minus, and when we multiply these, we have a positive 15. And we multiply these, we have a 0. So we have minus 15j. Plus, when we multiply the down diagonal here, we have a positive 15. When we multiply the up diagonal, we have a minus 0. So we have plus 15k. So that means our vector is -40, -15, positive 15. Now, in order to find the area of the parallelogram, we need to do the length of that. So let's talk about the length of A cross B. This equals 40 squared, -40 squared. I guess we'll be technical here. We should be always. -15 squared and positive 15 squared. So when I do that math, I get the square root of 2050, which becomes 5 times the square root of 82. So that's my area of my parallelogram, but I want the area of the triangle. So the area of the triangle is 1/2 times 5 times the square root of 82, which is 5 over 2 square root of 82. Now, WebAssign is probably asking for that exact answer, so be sure you answer in that method. You may want to pause and write this down. The problem says find A cross B and verify it's orthogonal to both A and B. So this is a problem from your exercises. So this is number 1 in the book, which is not one of the exercise ones. I'm not sure why. But we're going to start off with A cross B. Now remember, A cross B is the cross product of A and B, and it is orthogonal to vectors A and B separately. So we're going to do IJK. When you write your A and B in your IJKs, make it a habit to put the vector notation over it because it's required to be there. And if you build that habit, it will be a habit. So I filled in A and B, and we're going to write vector I times, we're crossing off the top row in the first column, so we have 3, 0, 0, 5, minus vector J, and we have 2, 1, 0, 5, plus vector K, and we have 2, 3, 1, 0. And now we're going to find the cross products. I literally draw my arrows to keep my face and my eyes going where they need to go. So it's a good habit to have. I know I say this every time I do it, but it's a good habit to have. Some of you may not need it. We'll see. All right, so we have 15 and 0. So we have 15i. And then we have positive 10 and minus 0. So we have minus 10j, and then we have plus 0 and minus 3, so we have minus 3k. So we're going to say that this equals 15, negative 10, and negative 3. All right, so this is our orthogonal vector. This is A cross B. I'm going to label it over here A cross B because it's important that you label your answers correctly. All right, now we need to verify it's orthogonal. Remember that two vectors are orthogonal if their dot product is 0. So we're going to take A dot A cross B. So A is 230 up here, and A cross B is down here. So 2 times 15 is 30. 3 times negative 10 is negative 30. And then 0 times anything is 0. So this gives us 0. Therefore, A is perpendicular to A cross B. And now we have to check it for B. Let's see if we can do this without losing it. So we have B dot A cross B. Remember that that the dot product is commutative, so you could do them in any order. So we're going to pick up these two. So we have 1 times 15 is 15, and 0 times anything is 0, and 5 times negative 3 is negative 15. Therefore, B is perpendicular to vectors A cross B. So that is good. So if you're asked to find a vector that's orthogonal, we do that by using the cross product because the cross product is orthogonal to both A and B. So that problem makes it feel like it may be harder, but it's not. So keep that in mind, and that it won't be too bad. If you think about the vectors I, j, k, I think it's a little obvious that I cross j equals k because k is orthogonal to both of them. And then j cross k is orthogonal to I, and k cross I is orthogonal to j. So that's kind of obvious there. What's not quite so obvious is the second half of the note. This is a note here. I guess we should mark it as a note. Let's do it. The second part, these are given. You can prove them if you want to later. J cross I, if you go in reverse, is negative k. Remember, it's that following the right hand rule because it goes this way. So your fingers need to curve this way so it's down. It's out of the page. So that's where the negative comes from there. And then if k cross product with j is negative I. And then I cross product k equals negative j. I learned this. This isn't in your book, but I learned it this way. You have vector I, vector j, vector k. So if you're going to do the cross product of these two, then you get the k down here underneath, and it's positive. So as long as you draw your arrow in a clockwise fashion, it's a positive answer. So let me do that again. I cross j equals k. You can see this here. J cross k equals I, and k cross I equals j. Now, if you go in reverse, it's the negative. So k cross j counterclockwise gives me negative I. And then j cross I gives me negative k, and I cross k gives me negative j. For some reason, we use that enough that the counterclockwise is the negative cross product. Counterclockwise is the negative cross product, and clockwise is positive. My W's have extra is a positive cross product. So it was something I had to learn at some point. So if you run across it, it's something that makes sense. You don't have to memorize it. But let's look at some properties of the cross product. First of all, because we're working with determinants, remember that the commutative property does not hold. So keep that in mind. So take a minute and pause and look at these properties of the cross product. the commutative property number 1 does not hold, but A cross B equals negative B cross A. It kind of makes sense. Number 2, we have a scalar multiplied by one of the pieces of the cross product. Number 3, it kind of looks like the distributive property. It's kind of the distributive property in a weird way. Number 4, more looks like the distributive property with cross products. Number 5, you have the dot products with a cross product. And number 6, you have a couple of cross products happening there. What's interesting to note is number 5 works out in such a way that we define A dot B cross C to be A1, A2, A3, B1, B2, B3, and C1, C2, C3. Notice that this is a dot product, which gives me a scalar. So I'm taking a vector here times dot product with another vector, so that gives me a scalar answer. And that's why this literally equals A cross B dot C. You can put the C at the bottom, and it works out in that way. So that one's pretty easy to see. And this value right here is called a triple product. And that's an important concept and an important note to make. You have a triple product. So it's called the scalar triple product of vectors A, B, and C. And it's written in this way. Also, this leads us into, let me scroll up a little bit. So we can use our triple product. And let's look at a parallelogram. Let's say we have vector A, vector B, and vector C. Now with A and B, we draw a parallelogram, and with B and C, we're going to draw a 3D parallelogram. Let me see if I can get it drawn while I'm talking to you here. I may not be able to have that skill. We'll see. It happens. It's called a parallelepiped, and the volume of a parallelepiped, you can see this parallelogram is the base, and then it becomes 3D, and it's called a parallelepiped. Parallelepiped. So it's a 3D parallelogram, and let's talk about the volume. So let's draw our height perpendicular here. Height is perpendicular to the base, so this will be our height. And for volume, we say the area of the base times the height. Now we know the area of the base is the length of the cross product of B cross C. And now let's talk about the height. So we have an angle between here and here, theta. So if you picture a right triangle, then we could find the height to be the length of A times cosine of theta. Now we're going to say the absolute value of the cosine of theta because theta doesn't have to be an acute angle, but we need it to be positive because volume is always positive. The height is always positive. So now we're going to say volume equals the area of the base, which is the cross product of B cross C times the length of A times cosine of theta. So if you remember your dot product, let me throw that in here real quick. So A dot B would be the length of A times the length of B times cosine of theta. So here we have the length of B. So instead of using the length of B, we're going to use B cross C. So we're going to say that the volume then equals, we could say, the length of A dot B cross C. Since we have the length of everything up there, we can put it all in the length and say, so we have the triple product and we have the length of that. That would give us the volume of the parallelepiped. So the volume of the parallelepiped is the length of the triple product of A, vectors A, B, and C. So it's our scalar triple product of the vectors A, B, and C. So if the volume is 0, that means that A, B, and C are coplanar. Let's say that we have A and B here, and we have the plane that they're in. So let me draw this plane here. If the volume is 0, then in some way, since the volume is 0, one of these vectors, it could be any of them, lie in the same plane. So I'm drawing C on the plane for A and B. Think of it as A and B form a piece of paper and C is lying on that paper. So we have a note that says, note, if the triple product A dot B cross C equals 0, then A, B, and C are coplanar. That's not something that you need to make huge notes of. It's not a big note. It just follows from the volume. It makes sense that if there's no volume, then there's no parallelepiped. Then A, B, and C are coplanar. So we have an example. And the example says, use scalar triple products to show that the following are coplanar. So rather than write all that out, I'm going to say, are they coplanar? We're going to let A be the vector 1, 4, -7. B is 2, -1, 4. And C is 0, -9, 18. So if they're coplanar, their triple product is 0. And if they're not coplanar, their triple product has a value. So let's find the triple product. 1, 4, -7, 2, -1, 4, 0, -9, 18. So this works just like before. I'm going to pick up the 1. It's a positive instead of the I, and I'm going to cross out the top row in the first column. So we have -1, 4, -9, 18. I'm going to say plus, not plus, we're going to say minus because this is in the same spot as the J. So minus and 4 instead of J. Cross off the first row and the middle column. So we have 2, 4, 0, 18. Then we're going to say plus -7. And we're going to cross off the first row and the last column. Now I'm going to draw my diagonals. I do them kind of in my head, but I think you need to see the diagonal lines and I need to see them. That's a wonky one. All right, so when we keep the 1 so it doesn't really affect life, we have -18 here. And this becomes plus 36 when we change the sign. So we have 18 minus 4 times this becomes 36 minus 0. So 4 times 36. Minus 7, we might as well do that. Here we have -18 minus 0, so we have -18. So when we take and do this value, we do get 0. Plug it in my handy dandy calculator. Therefore, vectors A, B, and C are coplanar. Before we do an application, let's look at a couple of the problems in your homework that might give you issue. So this first one says, find the length of U cross V and to determine if it's directed into the page or out of the page. So this is interesting because U cross V, you need to go back to your U cross V formula. So let's write it over here. U cross V equals the length of U times the length of V times sine of theta. And remember, the right-hand rule is going to help you determine if you're in or out of the vector. But the problem is it's the angle between the vectors. Notice that we're head to tail here. So what we want to do is we need to complete this parallelogram in order to be able to figure out if we're in or out of the whether we're going into the page or out of the page. So remember that this here right here would be 30 degrees from our high school geometry. And using corresponding angles, this is also 30 degrees. So this would be V over here as well. Now, we're going U cross V. That means we're going from U to V this way. So our right-hand rule means we're going into the page, not out of the page. So we know that we're going into the page. That's the second part because it's U cross V. So we're going from U to V. And then we're going to say the length of U cross V equals the length of U times the length of V times sine of theta. So the length of U is 4, the length of V is 3, and we have sine of 30 degrees. Sine of 30 degrees is the square root of 3 over 3. So we have 12 times the square root of 3 over 3, which is 4 square root of 3. This one was just interesting because we had to complete the parallelogram to get the U and the V to get the angle between them, because you weren't given the angle between them, you were given 150 degrees. So you tend to want to just run with that, and then you won't have the right answer. So pay attention to that. Let's look at another one. So the idea of the cross product occurs a lot in physics. One particular example is here we see the torque. The torque is this Greek letter tau. We write it as a capital cursive ET, and it looks like that. So what we have is we have a force F acting on a rigid body at a point given by a position vector R. So if we turn the wrench, we can see the tightening or the turning effect. And that effect is called the torque, and it's relative to the origin. So we define the torque as the cross product of the position vector with the force. So this measures the tendency of the body to rotate about the origin. The direction indicates the axis of orientation, and we can use our theorems that we know to say that the length of the torque or the magnitude of the torque vector is equal to the length of the cross product of R cross F, which we know to be equal to the length of A times the length of B times sine of theta. So all of those are used because this equals this. So you can use all of these in such a way. Theta is the angle between the position and the force vectors, just like it would be for A and B. The only component that can cause a rotation is F sine theta, the length of F sine theta. So, you still have all of the rules we learned about cross products coming into play here. So let's look at this. We have an example. So this example nicely comes with a picture, and it says a bolt is tightened by applying a 40 Newton force to a 0.25 meter wrench, as shown in figure 5. Now notice it always has to be newtons and meters. So the fact that we're in meters is good. Sometimes it's in centimeters and you have to change it to meters, so keep that in mind. It says find the magnitude of the torque about the center of the bolt. So you can see they drew all of these things onto a picture for you. Remember, we're looking for the magnitude of the torque. So we're looking for the magnitude of the torque. I like to make a note of what I'm looking for. And we're not given R, but we're given the length of R to be 0.25 meters. Nice that it's in meters. We don't have to change that. And we're given the force, we're given the length of the force, not a vector, but the length of the force to be 40 newtons. So that's nice and worked out for us. And then we also have theta, and theta is the angle between our position vector R and our force. So we can go ahead and say theta is 75 degrees. So we know that the length of tau, or the magnitude of our torque, is the length of R times the length of F times sine of theta. So this is a nice plug and chug problem. So we're going to say the length of R to be 0.25. Our force is 40, and then we have sine of 75 degrees. And we're going to plug that in our handy dandy calculator, and we get 9.66 Newton meters. 9.66 Newton meters. Now there's a note down here that says if the bolt is right threaded, then the torque itself is tau equals 9.66 N, where N is a unit vector directed down into the page according to the right-hand rule. So if it's turning to the right, then it'll be directed down into the page where N is a unit vector. All right, I want to show you one more before, I know this video is really long, I want to show you one more thing. A wrench 30 centimeters long lies along the positive y-axis and grips the bolt at the origin. So this is the origin right here. A force is applied at the end of the wrench, and it's 0, 3, negative 4. So it's about here. So my force is 0, 3, negative 4. Find the magnitude of the force needed to supply 100 Newton meters. So we have 100 Newton meters. That's our 100 Newton meters. That's the magnitude of our torque to the bolt. So what we're looking for here is we're trying to find the magnitude of the force needed. So we're given some interesting pieces. We're given the direction of the force to be 0, 3, -4. And we're given a 30 centimeter wrench. We have our direction of F, but we're actually looking for the magnitude of F, not just the length of F, but the magnitude of the force of F. So we're going to have to use, in order to find this, we're going to have to use the length of tau equals the length of the force times the length of the position vector times sine of theta. We don't have theta either, so we technically don't have our r direction either. So let's start with the length of r is 30 centimeters, which is 0.3 meters. So that means that if the length of r is 0.3 meters and it's on the y-axis, that means there's 0x. We have 0.3 for y and 0 for z. Now we can use our dot product to find theta. So a dot b, which equals the length of a times the length of b times cosine of theta. So we're going to rewrite this to say cosine of theta equals, let's say the length of r times the length of the direction of f, because that's what we're looking for here, is just the angle between them. And we're allowed to use that over the length of r times the length of f. And that's really what we're looking for. So let me move this up a little bit. So r dot f, we're going to say cosine of theta equals r dot f. So 0 times 0 is 0, plus 0.3 times 3 is 0.9, plus 0 over the length of r is 0.3, and the length of f is 9 plus 16 is 25. The square root of that is 5. So we have cosine of theta equals 0.9 over 1.5. I'm going to use my handy dandy calculator because I do not know that answer. So then theta equals inverse cosine, which gives me 53.1 degrees. Now we can talk about tau. So we're going to say the length of tau equals the length of r times the length of f. That's what we're looking for, is the magnitude of f times sine of theta. So this was just a direction vector. This doesn't give us the magnitude of the force. There's more going on with that. So our tau is 100 Newton meters, and our length of r is 0.3, and we're looking for the length of f, and we have sine of 53.1 degrees. Now you have to use your degrees symbol. I know it's weird because we know it's degrees, but WebAssign likes the degrees symbol. So we're going to take the length of f to be 100 over 0.3 times sine of 53.1 degrees. So then the length of f equals 416.67. And here we have newtons. So that's how we need to find that one. There's one more that's interesting. Let me show you one more. We have you look at this and you think it feels obvious, and it kind of does. So what you need to pick up here when you're looking at this bicycle pedal is the fact that this is 80 degrees between your position vector and your force. So as long as you keep that in mind, that problem shouldn't be too difficult. We did the hardest one first. It's good that way. All right, well, have a great day, and I hope you enjoy this video.